Okay, so session number 2. Like I showed in the kind of application video, this is we're showing how to analyze a stack of images instead of a single image. So a lot of the things will kind of center around that. We're going to start off by opening the image, displaying it, coming up with some kind of pause system to allow us to draw a box, and then we will go to actually analyzing the stack using the same VI that we did in the first one. We'll use the Labview built-in one because we just need simple information out for this. So, okay, to keep it as simple as possible for people that haven't even done as much as made a VI before, open up Labview and it does this. And if you just go to File, New VI, you'll get 2 panels that show up. You get the front panel and the block diagram. And for ease of manipulation, it's kind of good to have them both displayed at the same time. So if we just stretch one over to one side and the other one to the other side, so we can show both simultaneously, it makes life a little bit easier. We'll wait for a while. Okay, so we're going to be working with images, and so we're going to need to allocate room in the memory. We're also going to need to put a pointer in there to what file we're looking at. So to start off with, I'm going to keep this as simple as possible, so I'll tell you what I'm doing as I'm doing it. So if you right click on the front panel, you need to put a text control in to enter a file path. We can use a string. It's totally fine to use a string, but then you have to convert a string to a path name. So they give you, the option of using a file path controller. It's simpler. So if you click on that one, and then put it on your screen. So right click on the front panel, not the block diagram. Right click on the other side. Here. Okay.
You want to create new or?
Yeah. So you want a new VI?
Blank VI.
Yes.
And then you want what? Oh yeah.
Okay.
Text control.
Yep. All on the right.
Path. Yeah.
Yep. So you can do it with a string. If I did it with a string, you'll see that the outputs are different. So if I do a string, it goes pink. Okay, because that's what strings are. But if I do that, then I have to convert this text string to a path name. It's just it's how it classifies information. I mean, it's not a big deal. You just go to the string palette, go to convert, and go string to path. And just wire them through, and then you'll turn a string into a file path. You use this when you're writing to paths that your program is creating itself, because you obviously don't want to be making them straight from paths. But because we're using it to find the location of a file, it's totally fine to do it this way. Plus you get this really handy little click on folder thing, so you don't have to type out the path explicitly. You can find it. Okay, so we have a path dialog. We then need to create an IMAC, so we need space in the memory. So if you right click on the block diagram, you'll get, I should close my tools. I'll close you should get a whole list of a different list. If you go down to vision or motion, you might need to click on this downward arrow. I rearranged mine to be in this order, but you might need to click on here to see vision and motion. But once you do, as soon as we use this tool palette a lot, if you click on this little drop pin, it'll keep that one permanently open. So then we can, if you just right click on the screen, you'll always get the box up. As soon as you left click, it goes away. But if you've got any that you've activated the drop pin, they stay open. The same with any other palette. Some palettes you use a lot. If you want the numeric palette to stay open all the time, you can just do that.
But why are there so many functions missing?
So with yours, you didn't install all the packages.
Okay.
Can I just?
I should have don't have the vision in motion, and
Okay, well you're fine. You have everything that you need.
but it's just rearranged.
It's a little bit rearranged, but I have other packages for other things. So in yours, the only things that you really need for now are in this vision utilities. So they're all in here, image manipulation files.
Vision in motion.
Oh, okay, so you need to install it maybe, I don't know.
Where is it?
He has nothing in.
Let me see.
There's an empty box with this one.
Oh. Yeah, then you need to install the packages. So for now, you'll just have to watch it.
Okay. You're lucky.
Okay, so go to Vision Utilities, go to Image Management. Then here you have a whole lot of things to do with IMAC. IMAC just stands for Image Acquisition. You can do all kinds of fancy things to do with setting the image size and copying different sections of the memory and changing it. It's where you do everything where you need to control an image spacing in the memory. You can also give it all different names and things like that, but what we want to do is just essentially create a section in the memory for an image. So you click on it, drag it to put it in your desktop, and then right click on image name, go to create and constant. Okay, and then just give it a unique name, I don't know, ROI data or something, whichever, it doesn't matter. For ease of analysis later on, it's always better to tell it how much room to set aside. By default, it will automatically always set aside an 8-bit information frame. So it will set a U8 base. So if you if you hover over it, you'll get a little thing called image type. If you right click on there and go to create constant, you should get this little drop down box thingy. And as you saw, this is the default, which is 8-bit spacing. But because we want to open a color image, we want to click on it and change that to an RGB. All it really does is say, make more memory available. Because we want to do an RGB image, not a black and white image. If we left it as 8-bit grayscale, it would pull in an RGB, but it would just show it as black and white because it's essentially just using one channel. Okay, so now what we need to do is we need to connect, wherever this file path is, to read a file name and then put that data into this section of the memory. So if we go up on here and go to files, there's a little IMAC read frame. So it reads more or less any picture type into a memory place that we specify. So if you hover over it, you'll see the context help. So to bring up this context help, you go to help and then show context help. Just up there. So we need to wire in the things that are in bold. Like we had to from the first one, the two things that are in bold are the file path, because it needs to know what to open, and the image, which essentially says where do I need to put this in the memory. So we just connect those two things up. So connect the file path, connect the image, Alright, so now it will actually let you run the VI, because everything is fine. You're making room in the memory, you're opening a file. We're not displaying it, but you don't have to display it, we're just putting it in the memory. But of course we would like to display it. So what we need to do is come up with some kind of display pane. The easiest way to do this is if you go to the front panel. So if you click on the front panel with the left click and then right click, go to the vision palette and go to image display. And you get this big box and you can just drop it wherever you want to drop it. And then that's your... Okay?
There were two of them.
Yeah, go to this display or display classic. Yeah, just go to image
What is
display.
the difference?
One looks old and funky, and one has the new display. There's a similar things in lots of things with the front panel. You can choose the classic toolbar, which has like older style buttons, and the new one has modern style buttons. Okay, so you have this display, and then we just need to wire it up. So we wire up image out to this box. So then we're actually displaying this file. And at this point, you could run it, everything will be fine, it'll just show this image. So if I went to here and told it where to find, you know, a picture I want to show, you know, the VI will run totally fine. Boom, there's an image.
But now this happens what you told me, that it's somewhere in the memory forever.
Well, until we trash it.
Yeah, but you cannot trash it. Now,
I can.
From now on.
I can.
You can? Okay.
Because the thing in the memory has this name.
Ah, okay.
So if I trash a, if I action a trash file, I can either wire it to this name, or I can wire it for all IMACs.
Oh, okay.
So all memory locations which are written by the IMAC command, it will trash. Becomes problematic if you're running lots of things with sub VIs. So for sometimes you might want to use like pattern matching things or shape matching things or detection things, where you have to load an image to the memory. Then if you trash it, it deletes the pattern that you're trying to match from the memory while you're running, and that's not what you want. So then you have to wire them explicitly. But for this, we're fine. So, okay.
But now you could also like wire it to this load thing somewhere, or
I'm sorry?
there's no possibility to wire it right now.
To wire what?
This trash thing.
Yeah, so if so we're going to do it in a minute anyway, so we can do it now. So if you go to Vision Utilities and go to Image Management to get all these kind of IMAC controls again, you have this little trash can one, and it basically allows you to destroy all or destroy particular image locations that are stored in the RAM. So what we can do is this image out contains information not only of the image but also of what that image name is, so the pointer to the memory. So we can wire that straight to the trash can. But right now we'll have a competition on speed. That it's going to be trying to display this image at the same time that it's trying to delete the image from the memory. So that's not what we want. Right now we'll have a competition, and that's never a good thing. You'll kind of see.
Does Labview allow it?
Yeah, it's totally fine. So if you look up here, it says totally runnable VI. It'll be kind of a question of which one's faster, destroying it or showing it in this format. Because
But if it's destroyed, will it still show it? Or,
No.
or
it'll just
so it's a flicker for once and then it's gone.
exactly. If we had a loop, we would just see this constant flickering as it's trying to create it and destroy it at the same time. And it really depends on which function's being faster at that point, whether it displays it or destroys it. So, and you can get these competitions all over the place, so you have to kind of be careful. As I kind of mentioned briefly in the first one, and like I do a lot, if you see any of my VIs, I use this error string to determine order. So because one thing cannot action until all inputs have been read, essentially it cannot run this until this has happened. Well, it can't do that anyway because this is there. But for the example of these two, if I don't want this competition, I can do two things. I can create a sequence around it. So if I go to structures, there's this thing called flat sequence. It looks like a film strip. And it means if you draw a box over one thing, it kind of executes everything in this element before it can move on. So I can add another piece to this film strip. And then I can put something else in here. So if I wanted to put the trash can in here, I could put the trash can in here. Wire that guy in there. So now the two wires would essentially be the same thing, but it won't execute this section of the film strip until this section of the film strip's done. So now we've removed the competition. It will always display the image before it destroys the image.
Does it keep the image?
No, it destroys it.
So from your front panel you can see it.
Well, you can see a flash.
So what you really need is the stop button.
Well, no, what we need to do is we need to put it into a loop so that it will display the image while we're working, and then once we stop working, destroy the image.
Kind of a stop button.
Yeah, but we need to have a stop button, we need to be in a loop. We need to be actioning something. Right now, it executes once and once only. Remove sequence. Let's delete.
So how do you remove the
So if you right click on it,
the leftovers of the wires?
so you can like highlight them and like click delete, but the easiest way is to click Control B.
Okay.
Control B deletes all broken wires. When you're starting off, it's better to click the wire and delete it, because a lot of times, you know, you can delete something and there's lots of wires around that get broken. And if you hit Control B, you can have a whole bigger mess than you started with, because it might not have been like a big problem. You might have just had an extra wire kind of sticking onto something. And if you hit Control B, it deletes all wires that are to do with being broken. So you might actually delete most of your wires by doing it. So for these things, it's fine if we know exactly what wire is broken. But sometimes it's better to just select the wire and delete it. All right, so we're essentially doing a region of interest analysis. So we need the program to keep this program running and showing us the image, essentially on a time delay sequence. So the way to do that is with a while loop while it's displaying the image. So if you right click on the block diagram, go to structures and go to while loop, you can then draw a while loop over the image. And now it will just keep displaying this image as fast as possible until we say stop. Right now, it will, well, two things. One, you'll see that it's got a broken arrow, which means, look, we need some input. And if you click on it, it'll tell you exactly why it's saying that. So if you click on it, it should say, yeah, there's a conditional terminal which we don't have a wire to. And if we hit show error, it will highlight this box, which essentially means, look, we haven't wired the stop button. So we need to wire the stop button. So if you right click on the front panel, go to buttons, go to stop button. I'm going to stick a stop button on it. Okay, once we put it there, it came up here. We need to drag that one inside this while loop. And the reason it's inside is because we need it to read the state of this button while it's running. If it's on the outside, it will not read the state while it's in a while loop. In other words, you can have an infinitely running loop.
Is there any, why is it useful to do it on the front panel?
This
I
is,
did it just as a control for the web things.
that works too.
Okay, so it's no
Nope.
It's just workflow.
Yep, just what you now. Okay, so now at least this will stop when we hit stop, but the downside is this loop will run as fast as your computer can do it. In other words, it'll probably action it, 1,000 times per second. Around about a millisecond it takes to run these loops. So we need to put a time delay in there because we're putting this in there in essence to wait for our action. We need to draw a region of interest on the image and we need it to wait for our input. So we don't want it to be running as fast because we don't work faster than 30 frames per second, so we don't need this loop running faster than 30 frames per second. So we need to put a time delay in there. So if you right click on the screen, on the block diagram, and go to timing, go to wait, click on there, don't do that, and then right click on the little thing that says milliseconds to wait, and just create a constant, and we put something like 30 in there. Doesn't really matter what the number is. I mean, you could set it to whatever, 30 or 35, whichever one you want. Basically gives you it as real time. You can make it longer, and it displays it once every, however long do you delay it for. It's just there's no need to make your computer work harder than it needs to, and we don't run faster than 30 frames per second, so it's silly making the computer. If it's actually doing an analysis, we want it to run as fast as possible, then we don't put a time delay in there. But because this time delay is so that we can draw a box, 30 frames per second is fast enough.
Where does time delays came from?
So if you right click on the block diagram,
Yeah.
you should get something that looks a little bit like this. Then go to timing,
something different.
It's in programming.
Yeah, so if you click that one, yep, go to programming,
Programming.
yep, and then timing, go to wait. Just drop that on there, and then right click on the left of it so you can put a constant in there. And then it'll run it at 30 frames per second. Yep. Okay. So next thing that we want to do is, just like in the first one, we need to read out the region of interest that we draw. So we need to draw this box. We need to pull out where we've drawn this box, and we need to feed that into the little light bulb thing, or image intensity analysis (VI). So we need to get a parameter or a property node, should I say, from this display. So if you right click on the image on the block diagram, so if you right click on there, and then go to create, and then go to property node, these front panels do so many things. Essentially what we need is this ROI. So you kind of scroll down till you see ROI, click on that, and then we can just drop that on this one. If you hover over the ROI, up here it should tell you exactly what information is nested within this property node. In this particular property node, there's 2 bits of information. The contours side of things, you only really need to look at if you're doing something other than a rectangle. Like if you're drawing a circle or a rotated object, or if you're doing anything other than this one, you need to look at the contours of your box that you're drawing, because this is by far the simplest. All we need to know are the data points for the corners, so that's the one that we'll use. But again, if we hover over it, it says it's a cluster of 2 elements, and the one that we need is the global rectangle, and it's a 1D array. So we need to index this 1D array, which is the global rectangle. But first of all, it's a cluster, so we need to unbundle this cluster. So if you right click on the block diagram, go to cluster, and then go to unbundle. Click on that unbundle and put that on the screen. And you can wire this into there. So if you left click kind of close to the arrow, connect them up. When the data is when the VIs are named well, and you do like cluster bundling, the names actually carry over as well. So like here, I know that the first one's a global rectangle. I don't need to kind of look in here and see, okay, the first one's this. Okay, so it's a 1D array of 4 elements. So we need to index this 1D array. So you right click on the block diagram, go to your array palette, and go to index. And just wire it up so we can actually index this array. And if you go to the help menu or look it up, you'll see that a global rectangle or a rectangle essentially contains the 2 corners, the top left and bottom right, are the only 2 coordinates that you need to actually construct a rectangle. You need 2 data points. And all it does is it puts them in a line, so that, if an example is, if you have a box which goes from x1 to 1, 1 to 3, 3, then essentially you have a 1D array which says 1, 1, 3, 3. And we need to then split out this information, because this right now is just numbers in a line, and we need to index this line so that we can pull them all out. I've got 4 things there, yeah. Okay. And we need to tell it what index each one of these at. This array is quite nice because it's always the same shape, so we can put constants in each one of these points. So Labview starts at 0, so the first one's always 0. We then need to create 1, constant 2, constant 3. So you just kind of hover over it, right click, and go to constant, and then change the number until you get 0, 1, 2, 3. Yeah, Labview doesn't have a zoom mode. That's one thing that they really need.
How can you see which one you have? Now I see.
Okay. Yep. Does everybody have an index set? Okay. So, before we actually do this, we should have looked to see what we're trying to create. We're kind of getting ahead of ourselves. So if you right-click on the block diagram, go to Vision, and then we need to go to Machine Vision, and then Measure Intensities, and then Light Meter Rectangle. Click on that and put it on your page. So, measure intensities, yep, and then rectangle. Yep. Put that on page.
So this rectangle is the frame of the picture, or it's a selected?
It's a selected region. So what we're doing is we're drawing a box that we want to know the intensity from. So if we're looking at this image, let me just zoom out just a little bit. Let's say, I don't know, we've got an image stack and we want to know, maybe this spot's of particular interest, and you want to know if the intensity of this changes in a certain amount, in your image set. You want to know if it moves or if it spreads out, or if it changes intensity. What we want to do is we want to draw this box over this region and then say, look, tell me how the intensity in that box changes across all of my images.
Okay.
So
What are those indexes like?
These indexes?
Yeah.
So it's indexes for a rectangle. So you need 2 data points for a rectangle, top left, bottom right. And we can use previous knowledge, because I'll tell you exactly how it's formatted. It goes x1, y1, x2, y2. Okay, so I know that as I pull out this first one, it's telling me the x value of this corner. And then the next index down, which is index 1, is the y value of that corner. And then it's doing this one, x value and then y value. Okay, so then once I know this value and this value, I now know where this rectangle is. And the reason why we're doing this is because this kind of inbuilt VI requires a certain type of rectangle. It's this brown fat line, and if we hover over this, we've got a blue thin line. So a blue thin line is a 1D array. If it was a 2D array, it would be a thicker blue line. If it was a 3D array, it would be even thicker blue line. And here we have a moderately thick, so like a 2-line thick brown line, which means it's a cluster. So this is a cluster of data that it's expecting. And it's a different type, so we have to convert it in some way. So if we go to the detailed help, it'll pull up a little help panel telling us exactly what it expects. It's saying, look, in this cluster, it wants it in this format: left, top, right, bottom, and then a rotational angle. This, to most people, makes more sense because all the values for the x-axis, y-axis, they're all separated out. It's not a 1D array. The 1D array is just used now for convention because it's it's how it originally was done. This is, I suppose, a more modern VI where, this is how people prefer to see the data. So, but if we want to actually combine the two things, we have to write our own little conversion from one set to the other. So we need to separate out all of these coordinates, and then we need to bundle them together in the right format. So this thing says, okay, this is a cluster of these 5 elements. So if we go back to the block diagram, we need to build a cluster of these elements. So if we right click on here, then go to cluster, and go to bundle the cluster, we get this little kind of boxy thing. And just like we did with the index, if you grab the little tab on the bottom, we can make it bigger so we can put more things in it. And it expects 5 things. Just like the help file said, it's essentially 4 32-bit integers and then a double precision number. So we need to give it exactly that. If we don't, it'll say, look, there's a problem. So, but one of the conventions that does hold is it still numbers things in exactly the same way. So it's still x1, y1, x2, y2. So we can just wire the lines straight over. So if we go back to this one, and if we drag this guy down here, we can wire these straight over. And x1 goes to x1. But then we have to make a constant for the third thing, because we don't have a rotation parameter, because our box isn't rotated. We have to make an extra constant, because this will not work. So if I shrunk this a little bit and just made it 4 elements, and then wired this guy in, we'd get this little broken line. And up here, it also gives us a broken information. And if we look at the context help, so if we hover over this, the context help changes, and it says, look, we've connected together 2 things wrong. We've got 4-element cluster, and it's expecting 5 elements. So we have to change it from a 4-element to a 5-element cluster. So then we change this size to 5, but then we have to put a value of 0 in here. If you go to this, it's expecting a double point precision number, so that's what we'll give it. So we right click on here, go to numeric, go to constant, click it on the screen. If we wire up this constant, essentially now it's got a cluster of 5 elements and this thing's fine. It's of a different data type than it's expecting. So what we would do is right click on the constant and go to representation, and then change that to a double point precision number. Okay, and it goes orange. And if you go back to the help file, you can see, okay, it's expecting 4 I32s and a double point precision, and that's what we're giving it now. We're giving it 4 I32s and a double point precision. So the VI is happy.
This vision light meter came from which part?
So if you right click on the block diagram, go to vision and motion, then go to machine vision.
Machine vision, right? And in my vision activities.
Yeah, it's they have a lot of their kind of inbuilt like moderately complex VIs in machine vision. And then just go to measure intensities, and then light meter rectangle. Okay.
So it made these 4 lines plus. So these 4 lines get automatically blue because the IMIQ requires them to be in this kind of format.
Which one, sorry?
The one from the array elements.
This one to this one?
Yes.
Well, these ones are blue because this is blue. So the array is blue.
Yeah.
Because it's, the array which comes from this guy is blue. I mean, it tells you up here that this is a global rectangle of 32-bit integer numbers.
If I want to add a constant to this last...
To this one?
To the 0.
Yeah.
I cannot do it.
No. So
I don't know.
to this one? Yeah, so if you right click and try and add constant, it won't let you do it because it's a cluster. And a cluster contains any data. So you could put a true false thing there, you could put a string there, you could put a file path there, you could put an image there even. So it doesn't, just saying you want a constant doesn't mean anything to it because it can be any data type. So we have to, rather than specify, trying to tell it to create a constant, essentially it has no default for what a constant is. If it was just looking for a numeric thing, then it would give you the option to have a constant, but because it's a cluster, and a cluster can contain any data type, it does not know what it means. Anyway, so we have...
How did you get it there now?
So if you right click on the block diagram, and then go to numeric palette, or go to programming and then numeric. Yep, and then just go to numeric constant.
Okay.
Okay, and then once you've got that on the screen, if you right click on it, and then go to representation, you can change that to a dBl or a double point precision number.
Okay, then I'll wire it.
Yep, and you can wire it.
Do you have any idea how to ship this to programming? This XFS is kind of...
Yeah, it's a kind of annoying, isn't it? Yeah, you go into change visibility, change visible categories. So if you right click on the screen, I'm pretty sure it's in here, and you can kind of change what's visible exactly. Yeah.
You have this one open? And it goes in vision
Okay.
You just have to make it step. Then you get this view thing here.
Okay, so the next thing that we need to do is, right now it just looks at one image and reads an ROI. What we want to do is analyze a whole set of images. Okay, so the way that we do that is we can write a very particular program that goes, from this file palette to actually analyze all the files that are within a folder, but there's actually a little VI to do it. So I'm going to show you how to do it using the Labview VIs, because a lot of times it's a lot quicker. But the first thing we need to do is find out where this path is. So if you right click on the block diagram, go to File, Input, Output, and then go to Strip Path, because we don't want the full path. We don't want the file path with the file name on it. We just want the file path. So if we go to Strip Path, just drop that on your screen, and then just wire in where this path is. Now what it's doing is it's giving us the path, and then if we wanted to, we could read out the file name that we chose to, but we just want to know this file path. Okay, so now what we want to do is we want it to essentially give us a list of all the files that are in this file path. So if we right click, go to File, Input, Output, then go to Advanced File Functions. At least I think it's in here. Is it still in here? Yeah. Okay, and you want to recurse the file list. All right. So essentially, tell us what files are in this folder. It actually can do a whole lot more than what we're going to ask it for. Just wire in the strip path to the folder path. These two things down here, like the pattern and the folders to exclude, actually allow you to be very selective about what files it reads. We can put in a particular pattern for the file name, like if there's for the confocal images, for example, it can have in the file extension somewhere telling you which channel it's reading from, like say CH01 or CH00. So if we just ran all things, then we'd get like kind of flashing colors as we analyzed it. But we can say, if we want to analyze just the green channel, we can say look at CH01, and then if it doesn't say that in the file name, it will never put it in the file list. And we can do it with folders too. We can set subfolders, and it'll actually do a lot more. For now, we're just going to read everything. So right now you have all these.
It took me quite a while to figure out why my example doesn't work.
Yeah.
Or your example doesn't work on my computer. I had some
all the files in there.
Labview files in the folder.
Yeah. Yeah, you have to. If you want other files in the folder, you have to give it some pattern. You have to say like it has to be a certain type of file. Okay, so if you kind of hover over here, it'll give you some options, and if you look up here, it tells you what to expect. And what we're going to use is this kind of array of information here, which tells us all the files in this directory. We wanted to run this VI on all of the files that we're using. So we need to do this little light bulb thing on every single file. And the way that we do that is we run it in a for loop. So we need to action it on every single file. So if we drag this guy into a little bit of free space, hopefully your wire stays connected. If not, reconnect it. Then right click on the block diagram, go to structures, and then we're going to draw a for loop. So if you click on for loop and just draw it over the top, you should have something that looks like this. Then what we're going to do now is on the left side, here what we're doing is opening one image. We're opening that image so we can draw the box. Now what we want to do is open up all of the other files in sequence and do this analysis on the box that we chose in the first part. So we need to make some more room in the memory for a new type, a new iMac. So there's a little shortcut to make things a little bit quicker. So if you highlight a section, just draw a box over it. Then while holding down Control, drag it off there with the left mouse button, and it'll duplicate the information. So you don't have to go and grab all the bits again. Then all we need to do is just change the name, because the name has to be unique, else it'll override it. Okay. So one thing that this VI will only do, and you can find it out from the help actually. Well, let's see if it's actually there in the help. See if it says. No, it doesn't say. But one thing that you'll find out if you wire it wrong is you'll get an error. This VI requires single channel information. It can't tell you the intensity of an RGB image because it doesn't know which thing you want the intensity value from. You've got too many independent values. So if you have an RGB image, you either have to split the image, so separate out the color channels, and then tell it which color channel to look at independently, or you can just wire it up as a grayscale and then look at the grayscale value. For this, we'll look at the grayscale value, but if you're reading it from, let's say, the confocal, the way to do it is to actually separate out the red channel from this image. It would be more ideal if you outputted gray images for each channel on the confocal, but people have a tendency not to like doing that. So you can essentially take these and make them grayscale. This one was done with a color camera, so that's fine. But we can essentially just separate out each of the channels individually and then apply it to just one channel. So the quickest way to make a color image to a gray image is just to change the memory allocation. So now if we read a color image into this space in the memory, it will make it a grayscale image.
It will use all channels.
Yeah, it'll do just like a typical. It'll treat it exactly the same way that it would do, let's say, in Photoshop. If you right click and say make grayscale, it does use all channels. If you know that, like this was done with the color camera, so technically you should do it this way, rather than extracting one of the channels, because we don't know if it was coming from a different color channel. But if this was done on the confocal, where essentially it's a gray image, it then maps it to a color, then we'd need to extract the red color pane. But because this was done on a color camera, then this is a better way to do it. If it was on the confocal, extract the color pane. And I'll show you how to extract the color pane, like maybe next time, maybe the time after, when we use the confocal images as an example. So anyway, we've got this file list. We now need to open up all these files. So just like we remade this memory spot, let's just remake this guy. So rather than trying to search for it again, just hold down to Control, click on it and drag. And we'll drag that inside here. Just like at the start, you know, we have to tell it where to put this. You know, we've made this little memory location, so you now need to wire this memory location into that VI. One thing to note is, because we're naming this memory location outside of the loop, it's just going to keep overriding the same memory location. So it'll just keep overriding it. Okay. Okay. So this is essentially reading a file. I'm putting it into the memory, just like it was at the start, where we've got a file path and it's reading it and putting it into the memory. And we have a list now of all of the files that are in there. So if we click on the all files in directory and we drag that all the way to where it says file path, and just click, you should see, one, that this thickness of the line changes. You go from a double thick line to a single thick line, and you also have this little like kind of double bracket thing. And as you hover over it, it stands for auto indexed tunnel. Essentially, rather than you having to tell it how many frames there are, and that for each time it runs around the loop, it should increment essentially the number in the file list, it does it for you. So you don't, if you have an array of objects and you run it straight into a loop, it will auto index. If you don't want to, you can switch it off. So if you right click on the little double bracket, you can disable it. If you wanted to run on the whole file list simultaneously, that's what you would do. But what we want to do is open up the files individually, so we allow this indexing. Allowing just one thing to auto-index also means that you don't have to wire a loop number. It automatically knows how many times it has to run around this loop because it knows how big this array is. As soon as we wire this to here, it knows how big this array is, so it knows how many times to run this loop. You don't have to run it that many times. We can wire a constant here, go to create constant, and just say, look, we only want to look at the first 100 files in this file list. And sometimes that's what you want to do, especially if you've got a massive amount of files. Maybe you just want to look at the first percentage or two. That kind of functionality is used more when you're running real time, but your folder contains, let's say, 10,000 files, and you only need to know if it starts to decay correctly. As long as you're hovering over the bit that's decaying correctly, we don't need to tell it to run every single file. But for this, we want it to run every single. Okay. So now we want to wire this image out onto this this pixel intensity meter. So click on there, click on image. Okay, now this is going to apply this VI to this image. And then as the loop runs, it will increment. So it's like, okay, the first image, it will measure it. And the second image, it will measure it.
So in the second loop that we made, in a pathway, we use only the folder that all images are included.
Say that again.
In the second loop,
Yep.
we want to say that do this
Do this, yeah.
for all these images.
All those images, yep.
So we need to give the program the folder
Right.
instead of one image.
Right. That's what this does. So what we're doing is we're essentially saying choose a file,
Okay.
which is this one. Okay, so we choose a file and it displays that file. Okay. Then what we do is we strip the path. So you have, just like in a regular file path, you have forward slashes, etc. And then your last section after the last kind of location says what that file name is. Well, this one just takes off that file name. So if you hover over it, it returns the name of the last component of a path. So it gets rid of that file name because we don't need it. And then, so essentially, for want of a better word, this takes a file location and tells you the folder that that file was in.
Okay.
So now we know what folder is, and then this thing says, okay, what's in that folder?
Mhm.
So then we create an array of file paths that are in that folder. So if we put a little indicator thing here, it would give us a list of every single file that's in there. And then when we wire that to this loop and allow it to index, it then just treats it as an ordered list and then does it one by one. So you don't have to.
How the order is determined?
So in this case, it's determined numerically. So it.
But what happens if you get the two arrays coming to follow? How does it understand which one to cycle, or it cycles everything?
It'll do it for the largest number. And if it runs out of data, it will give you an error. It'll say that the indexes are not matched. So if I
Okay, so
wired
if
in,
you got one array and another array, then it starts to go through both of them.
Mhm. So if you
They
run,
have to be the same size.
no, they don't. You can run them at different sizes. It's just once the smallest one finishes, you'll get an error and it'll stop.
Yeah, okay.
Okay.
Because it'll say, look, there's no data in this array.
Maybe it's not a good idea.
Yeah, no, you shouldn't. It'll just, so there are ways to get around it. Sometimes you do want to have two, if you've got two arrays with different data in, you might want to run them all together. And then when one finishes, just put a value of 0 in.
Yeah.
So you can put a condition on there that says, look, once you get to loop number as big as the array size, the value now equals 0. So you can put a little Boolean function in there to allow it to run. Yeah, it will allow you to run arrays of different size into it. Okay, so right now we're doing everything right, and like the little arrow says, everything's fine. We don't have any errors. We have a couple of problems. One, we've got to clean up our memory, so we can drag our trash bin to the end, and we don't want our trash bin to action until everything else is done. And since this is the last item that's being done, we can run this error wire into there. But whenever you output something from within a for loop, it will automatically try to index it. So, because there's going to be a lot of items coming through there. So essentially, what you want to say is, like, I don't need to know on what loop number the error came from. So you disable the indexing, and then it's fine. Because a lot of times there's no need to know, that the error happened on file number or whatever. It's more there was an error, and that's all you really need to know. And doing it this way means that this will only be actioned after this finishes. If we were being picky with our images, we'd wire a different trash can for every iMac that we created. But if you know that you only have iMacs that you created and you need to destroy them in the memory, you just right click on the all images and just create a constant, so that you can say, look, destroy all iMacs that I made, and then it'll trash them all from the memory. Okay. So if we go from left to right now, we're opening an image of a particular file path. We're displaying that image in a loop until we finish drawing our box. Then once we hit stop, or we can rename this whatever we want to, like, it's okay. It finishes this little section and then keeps going. But the problem that we have right now is if we look at this, it will run these two things in sequence. So it reads the path and then starts to display the image. At the same time, it will strip the path, it'll list all the file names, and it'll run this thing at exactly the same time, because it runs things in a wired sequence, and we don't want it to do that. We don't want it to start analyzing this data until we've chosen our box. So the way that we can do that is, again, with the little error thing. We can use the little flat sequence, the little film strip, but the easy way to do it is just to thread the error. So we click on the little, if you're over here, you click on something that has to happen first. So you click on the error, drag that, and then click it on the side of the loop, and then click the side of the loop into the ROI. And what that does is, if you follow it backwards, this loop here requires data from these things, which requires data from the ROI, which now, because we wired the error, requires data from this loop. So we cannot read data from the ROI, which means nothing after the ROI will action until we say okay and this loop stops. If we didn't have this, it would run this before we even do our box. So this is just a kind of a quick way of determining the order. Lots of people will use these different structures to do exactly the same thing. You can run flat sequences, which determines an order. You can run stack sequences, which is exactly the same, but rather than being a film strip, it's like pages in a book. You can do all other kinds of things. You can run them into time sequences or that have wait for particular actions. But by far the easiest way is to just string an error line, because it can't action until that's been finished. So, okay, so we now determined the order. This should run, reasonably in order. The last thing that we need to do is, get an output. So, what we want to do is just figure out some kind of information out of here. So we have, these are your outputs. You can have histograms for this region, lots of other things, but most of the information is in this gray level intensities. And just like the input, we have the same kind of color, same thickness wire. So what that means is it's a cluster again, and we need to break out that cluster. So if you right click, go to cluster palette, go to unbundle, and drop that on the screen, then wire up that to that, and then you should see this little separate out. It automatically resizes itself to fit the cluster that you wired into it. And if you hover over them, it tells you what's in that data stream. For this example, we're kind of interested more in the mean intensities. So we drag the mean intensities to the edge of this box, and you should see this little auto index tunnel thing show up. And this time we want this auto index tunnel because it will now keep everything in order for us. And we just want to kind of see what it is. So if you right click on it and then just go to create indicator, it'll now have a little thing pop up, and this array is just this array, it just has all of these values in order now, and each number represents a different frame. But what also we would like to do, just like I had in the example, is just display it on a graph, because generally that's an easier way to look at things. So if we just find an open space on our little diagram, you right click on your front panel, go to graph indicators, and just go to chart. We just want a simple chart of all of the intensity values. So you click there and just drop it on your screen. Here you have your little block diagram, and we just wire in that value. And if you hover over here, it gives you some kind of information on what data type this will allow it to morph into. And if you want multiple plots, it also gives you a little hint of how to make them. It's like, okay, you have to cluster them up and then show each data stream as a different cluster, and then it'll compose it. Okay, so I think that's everything apart from making a little progress bar. The one that I had built in the example was a simple percentage, progress bar. So the way that we did it is we just make a simple progress bar on the screen. So if you right click and then go to numeric indicators, and you can kind of choose whichever representation you want. I mean, you could have a speedo dial if you really wanted to, but we just have a little progress bar. Make it a little bigger so we can see what we're doing. Okay. and that shows up down here. And we need this to change, you know, while this loop is running. One thing to note is that here it says U8, which stands for unsigned 8-bit integer. What that means is you can't have a big value bigger than 256. If we wired this straight into I, so if we did this, then it would get to 256, then it would go back to 0. So you kind of go all the way to the end of the progress bar and start again, and then keep going. If you were going to do this, you'd want to, one, change this representation. So you'd right click, go to representation, change it to like a 32-bit integer. Then once it's a 32-bit integer, you'd also have to set the upper and lower bounds for the... there are lots of ways to do it. The easiest way to do it is not to wire in I, but actually show it as a percentage of completion. So the way that you do that is I is the loop number, and this little thing over here will also output how many files there are. So we can just do a simple, you know, I divided by this value. But since I can be 0 to start, we don't want to have any...
Can I also use n for that?
yeah.
Should it be also the number of files? Like coming from this little
I don't know if it...
indexing thing.
I don't know if it will actually do it.
But there is no problem, I guess, if it's a 0, because then the loop will be executed 0 times, and if your operations are inside the loop, they will never be executed.
No, he wants to know if you can use n instead of this file number.
Yeah.
I mean, you can... I don't know... You know, I don't know. I don't know. I mean, we can stick an indicator on here and see if it actually outputs anything. I don't know. Maybe it outputs it. I have no
Then it
idea.
should output just n, the number of files.
Yeah, but you see, we haven't explicitly told it, so I don't know if it'll output it. We can create an indicator and see.
Yeah.
Yeah, the way I would do it is essentially go to numeric palette and add 1 to I, so that your first one is 1, you know, got 0 divided by some value. I mean, it's fine, it's just 0 divided by some value in some functions doesn't fly too well. And the same thing, if you go to the numeric palette, you know, you're just doing a simple percentage operation. So we need to divide, you know, what the current run number is divided by the total number of files. Go away. And you know, we just multiply that by 100 to give us a percentage. And for the value of 100, because we're doing the percentage, you should put it outside of the loop. The reason being, if it's outside the loop, essentially it's already in the it's in the loop kind of structure, so it's just pulling it from the data train each time. If we have it inside the loop, it has to read the value 100 and then it actions upon it. If it's already outside the loop, the value can't change, and since it's a constant value, you should try and drag them all outside the loop. And then you just wire that up into this guy. And essentially now you have a percentage meter for the progress bar. Simplifies things rather than having to set upper and lower bounds and ranges and things. But I'd be intrigued to see if numeric actually has data in it. I don't know. I have never done it that way. Well, you know, we can just run it and see what happens. Where's my stuff? Yeah, so it does work. So you can just run it from n. So if you're... I wouldn't actually do it that way, but because it's not efficient. But if you had a... Because you're now reading a function inside of the loop. You want to do it from an outside, so then it becomes a constant. So if you have the option, you want to have all your constants outside of the loops. So you never want to have something of a constant value being read inside a loop, because it's having to read that to a variable, essentially.
Yeah, but you have to put it in anyway, so it's just basically the same thing.
Yeah,
So you
I don't
put,
know.
You put this n number in
Yeah.
with the index of the
Well, I don't know.
this,
I don't know.
file. List.
Right. I don't know where it's going this from. I don't want it to be reading this each loop. And if it's inside, it might be reading each loop. Can you see what I'm saying? I don't want
Right, but it will, anyway, it will read the number you put in.
You'll read this one, yeah, but wiring it from a constant outside is a faster, more efficient way of doing it than reading essentially a new parameter. I don't know if, if I had 100 in here, it would have to read the value 100 in each time. Whereas if it's from the wire, this is a lower memory load speed operation.
But if you're in MATLAB, you define all the constants outside your loop, and then you use them in the loop.
Exactly.
You don't define them
In
in
the
the
loop,
loop again.
It's the same thing. Same thing. I just don't know, but I just don't know where it's reading this. It might read it first, so then it doesn't matter.
I don't know.
I don't know, but it's actually kind of handy. I didn't know that it would do it, because if you have something outside, not all things allow you to list how many files there are. Normally you have to create a little thing that tells you how big the array is. So if we didn't have this and we didn't know of this, you can just go to the array palette and then look at the array size, and you can just feed the array size in there, and then it tells me how big that array is, and then I could read that value in as a constant. And that, yeah, go ahead.
Or can you directly wire this output that you put there
This
into
one?
the end?
Yeah.
No, from the, no, not from there.
This one?
The blue one, yeah.
From the, yeah.
Yeah.
Wire.
So-
Because then if you put the array in, then it runs it as long as the array goes.
Yep.
And it does it then automatically. Otherwise, you would have to tell it.
Right.
from-
So
from-
if you can do for loops on defined data sets. I mean, it's quite common that you might actually have an array of data, but the actual thing in the loop requires the whole array, and you have to pick points from within the array, and then you have to have a different value. There are lots of times where the array might actually be an image. So you obviously don't want to index an image pulling it into the loop. So then you switch off the indexing as it goes into the loop, and then you index the array within the loop. But anyway, it seems to work. So yeah, that's how the intensity changes. The slider worked fine. The one way to see if your memory management was correct is that after the VI finishes, your screen should go gray. It means it deleted that image from the memory. If we don't delete, so if I just, switch this guy false. Oh, actually, I can just stop it. So if you stop it, or if you don't, clean up all the images, the image will stay on because it's still got a position in the RAM, so it still can display this image. But if we run the VI correctly and we've done our memory management efficiently, once it finishes doing the analysis, it should wipe that from the RAM.
And now, does it wipe the whole series of images, or does it
Wipes everything.
wipe every image individually?
No, it wipes it at the end. So it waits till it's done and then it destroys it.
So memory is filled with 300 something images.
Not in this one. So if you look at the extras in the server and actually go to that VI, it actually displays how you do exactly the same thing in real time. So if I quickly, because this one's done. So if I save this as session 2. Let me close this one. So if I open up the other example, Labview 2. then this VI actually preloads all of the images. So this one does actually make 345 sections in the memory. It's got a slightly different structure, and there's a little video on the server about how it's being built. Runs in a similar way. If we run it, we can choose our location for the data. So this one is, and then pick the frame you want to look at for analysis. So let's say this one. Okay, one of the things that you'll notice is that I chose it and it didn't show me an image. And if you look at the back, kind of area, I've got a delay on here. So if I go to the block diagram, I'm delaying it right at the start for actually showing, waiting for a file path. And the reason is, actually I'm running two things in parallel, and I need to make sure that the file path is correct. So, essentially I'm allowing people to load the file path, and rather than showing something straight away, it's like, are you sure it's okay? And if you're sure it's okay, you hit okay. If you're not, you re-choose it. And because what it does is it displays the file and lets you draw the box and move it around while it's running all of the images into memory. So if I hit OK now, I have this, but if you look down here, it's running things in the background. So I can move this guy around and choose things, that I want to look at. I may want to look over here, but all the time it's running things in the memory. So because it's running two things simultaneously, I need to make sure it's right. Else you're going to load a lot of things to the memory that you don't want to be there. The difference is, if you see over here, it's already giving me the trace. And if I grab this, I have real-time feedback. So this is the frame number of all the images. So in this one, rather than actually processing them all, individually, so loading the image and then processing it, I'm preloading everything into the memory and just, doing the analysis in real time. So it's still going through all 350 images, but right now it's doing all 350 images 20 times per second. So it's analyzing all of them 20 times every second, because that's my delay on the back end. So if I go to the block diagram again, I can either hit the light bulb so you can see where I am. So over here you'll see, okay, it's running through this right now. But every 50 milliseconds, it reruns this loop. And it's doing it on everything that's in the memory, which is all 350 images. So you can change how it works. Sometimes you don't need all of the files like crazy quick, but if you're doing, let's say, 10,000 files, it's going to be pushing it to do it real time. So what you could do then is limit the loop. So what we could say here is still pull in all the data, have, just like in the previous example, this kind of light bulby thingy, but we action it later on. But we put a limit on here and say, look, I just want to see how the first 500 files look. And then in real time, you'll be able to look at the first 500 files. And if you're seeing the right kind of information, you go, okay, that's where I want to be. But if you're, if you're looking for a particular event kind of a thing, maybe this event at whatever frame 150 means that something happened that you didn't want to happen. Well, you're in the wrong spot. You want to keep moving around until you find the spot. Essentially, it allows you to keep hitting the right button. We want to move this guy around and find the location that works best. I don't know. It's kind of an arbitrary data set to do this on, but essentially all you can see is that there is a different way of doing it. We can run it real time if that's what you want. And for some things like this, if you're looking for particular events somewhere in the file set, this is a more efficient way of doing it than actually drawing a box and then do all of the images, because a lot of times you don't know if you're in the right location or not. This essentially gives you a much better idea of what you're doing. And then once you're done, you hit this and basically it just finishes the file. But again, this screen goes white or grey or whichever color it is, which essentially says I cleaned up all of my data when I finished. I don't have any images still in the memory. But on the server, there's a description of what this is doing. If you actually compare the data, it's almost exactly the same structure. It's just actioned in a different order. Just changing the way that the loops are done to do different things at different places. But there's very little difference between the two. So I mean, you can have a quick look, watch the video and see how they differ.